Hello everyone, today's topic is Cauchy's residue theorem. Statement for the Cauchy's residue theorem is if f of z is analytic within and on a closed curve C except at a finite number of poles z1, z2 so on zn within C and r1, r2 so on rn be the residues of f of z at these poles, then integral C f of z dz is equal to 2 pi I into r1 plus r2 plus so on rn, or integral C f of z dz is equal to 2 pi I into sum of the residues at the poles within C. Means that here z1, z2 so on zn are the poles and r1, r2 so on rn are the residues of f of z, and f of z is analytic within and on a closed curve C except at a finite number of poles. Poles means how to find the poles? We are equating the denominator to the 0, then find the poles to the given f of z. So that poles within C, then we can find the residues r1, r2 so on rn. So by using the poles and residues we find the integration of f of z, that is 2 pi I into sum of the residues. So examples are: evaluate integral closed integral over C 4 minus 3z by z into z minus 1 z minus 2 dz, where C is the circle mod z is equal to 3 by 2 using residue theorem. First we have to discuss about the given region mod z is equal to 3 by 2. Means that this is a circle with center at 0 and radius is 1.5. 3 by 2 value is 1.5. So we are comparing with mod z minus a is equal to r is the radius, a is the center. So z minus a is equal to z, means a is equal to 0 here. So center at 0, 0 and radius is 1.5. We can draw a circle with radius 1.5. So this is the given region. After that we can write f of z is equal to 4 minus 3z by z into z minus 1 z minus 2. Poles find by using denominator equate to the 0, then z is equal to 0, z is equal to 1, z is equal to 2 are simple poles. These factor powers are 1, so that's why we can write it is a simple pole. Each and every pole is a simple pole, so that's why z is equal to 0, z is equal to 1, z is equal to 2 are simple poles, and z is equal to 0, z is equal to 1 lie within the given circle mod z is equal to 3 by 2. Because of here a radius of the circle is 1.5. In this circle we have z is equal to 0 and z is equal to 1. These 2 points are inside and z is equal to 2 is outside the given circle. So that's why we can find the residue at 0, 1 only, because of the residue theorem is applicable for inside poles only. So then it is enough to calculate the residue at z, 0, z equal to 0 and z is equal to 1. Now the formula for the residue at z is equal to a is limit z tends to a, z minus a into f of z. That is f of z is equal to residue of f of z at z is equal to 0 equal to limit z tends to 0, z minus 0 into 4 minus 3z by z into z minus 1 z minus 2. Here z minus 0 means z cancel. Apply z tends to 0. We get 4 minus 0 by minus 1 into minus 2. That is 4 by 2 value is 2. That is first residue R1. Next residue at z is equal to 1. Limit z tends to 1. Z minus a, z minus 1 into f of z. 4 minus 3z by z into z minus 1 z minus 2. Z minus 1, z minus 1 cancel. Then apply z tends to 1, that is 4 minus 3 by 1 into 1 minus 2, that is 1 by minus 1, value is minus 1. So residue 2 R2 is minus 1. By using residue theorem, integral C f of z dz is equal to 2 pi I into sum of the residues, that is integral over C 4 minus 3z by z into z minus 1 z minus 2 dz is equal to 2 pi I into sum of the residues at z is equal to 0 and z is equal to 1. that is 2 pi I into R1 plus R2, that is 2 pi I into 2 minus 1. So 2 pi I into 1 is 1, 1 into 2 pi I value is 2 pi I, that's it. Evaluate, next example, evaluate integral over C tangent dz where C is the circle mod z is equal to 2. So the given region is a circle with center at 0, 0 and radius is 2. So f of z is equal to tan z right as sin z by cos z. So denominator cos z equate to the 0, then we can get the poles, that is plus or minus 2n plus 1 into pi by 2, because of cos is 0 for pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2, all odd pi by 2's are equal to the 0 for cos, and cos of minus theta equal to cos theta, cos of plus theta equal to cos theta. So that's why we can get plus or minus 2n plus 1. So into pi by 2, n is equal to 0, 1, 2, so on. But we need inside poles only. So out of these poles, only z is equal to plus or minus pi by 2. So you can find the pi by 2 value to the real by using pi value 22 by 7. 22 by 7 by 2 means 22 by 14, value is 1.570. So that is plus or minus plus 1.57 means here it is nearest to the 1.5, and here also it is minus 1.5. So both the points are inside plus or minus pi by 2 are inside the given circle mod z is equal to 2. So first one, residue at z is equal to pi by 2 equal to limit z tends to pi by 2 z minus a, z minus pi by 2 into f of z sin z by cos z. If you apply pi by 2 directly, we can get 0 by 0 form, that is 0 into sin pi by 2, 0 by cos pi by 2 is 0, 0 by 0 undefined form if you apply limit directly. That's why we can use L'Hospital rule. You can differentiate numerator and denominator separately, that is uv dash. In the numerator we have uv, so you can apply uv dash plus v u dash, that is u z minus pi by 2 into v dash, sin z derivative is cos z, plus v into sin z into z minus pi by 2 derivative is 1 by numerator derivative is completed, denominator derivative cos z derivative is minus sin z. Now you can apply z tends to pi by 2 here, z minus pi by 2, z value is pi by 2, pi by 2 minus pi by 2 is 0, 0 into something is 0, plus sin pi by 2 value is 1 by minus pi by 2 value also minus 1, 1 by minus 1 value is minus 1, that is first residue R1. So residue of f of z is equal to pi by minus pi by 2 equal to limit z tends to minus pi by 2, that is z plus pi by 2, because of z minus of minus pi by 2 sin z by cos z. Again you have to apply the L'Hospital rule. We get z plus pi by 2 into sin z derivative cos z plus sin z into cos z, sin z into z plus pi by 2 derivative is 1 by cos z derivative is minus sin z. Then apply the limit minus pi by 2 plus pi by 2 0 plus here 0 into cos pi by 2 value is 0, so completely it is a value 0. Sin of minus pi by 2, sin of minus theta is minus sin theta, that's why we can write minus sin pi by 2 by minus of sin minus sin of minus pi by 2, we get minus of minus sin pi by 2, that is minus of minus 1 plus 1, minus 1 by plus 1 value is minus 1, residue 2, that is. Next, by using residue theorem, integral over C tan z dz is equal to 2 pi I into sum of the residues, 2 pi I into R1 plus R2, that is 2 pi I into minus 1 minus 1. So minus 2, that is 2 pi into minus 2 minus 4 pi I. Next problem is evaluate integral over c z minus 3 by z square plus 2z plus 5 into dz, where c is the circle given by modulus of z plus 1 z plus 1 plus I equal to 2. Here the given region is comparing with modulus of z minus a equal to r. So here radius is 2 and z is equal to a, means z is equal to minus 1 minus I. So x plus iy is equal to minus 1 minus I. So x value is minus 1, y value is also minus 1. So that's why z is equal to a equal to minus 1 minus I. So that is center a equal to minus 1 comma minus 1. Center at minus 1 comma minus 1 and radius is 2. This is the given region, circle, center at minus 1 comma 1 and radius is 2. So given f of z is z minus 3 by z square plus 2z plus 5. Here you can find the poles by using the denominator equate to the 0, but for denominator factors are not possible, so that's why we are comparing with ax square plus bx plus c is equal to 0. Here a value is 1, b value 2, c value is 5. Roots of this quadratic equation are poles of f of z, that is z is equal to b value minus 2, means minus b value is 2, minus 2 plus r minus under root of 2 square minus 4 into a value is 1, b value is, here we are substituting b square minus 4ac, c value is 5. So by 2a, that is minus 2 plus r minus under root of minus 16 by 2, that is equal to minus 2 plus r minus under root of 16 I square, because of I square value is minus 1. So we are substituting minus 1 is equal to I square by 2. We get minus 2 plus r minus 4i by 2. 2 common in the numerator. 2 into minus 1 plus r minus 2i by 2. 2 cancel. We get z is equal to minus 1 plus r minus 2i, means we get poles are z is equal to minus 1 plus 2i comma minus 1 minus 2i. By using this poles, we write the factors to the given equation is z plus 1 plus 2i, means this pole taken to this side, we get z plus 1 plus 2i into this pole. If you use this pole, z is equal to minus 1 plus 2i, we get this factor z plus 1 minus 2i, means z plus 1 plus 2i into z plus 1 minus 2i equal to z square plus 2z plus 5. So now which poles are inside we have to find now by using the given region. Here given region is modulus of z plus 1 plus I is equal to 2. So given region comparing with mod z minus a is equal to r, radius is 2 and a is equal to, means z is equal to a equal to minus 1 minus I, means the center at minus 1 comma minus 1, means x quadrant 1 and y quadrant value 1, and means x is equal to 1, y is equal to also x is equal to minus 1, y is equal to minus 1. So center at minus 1 comma minus 1. So and radius is 2. Now draw the circle with center minus 1 comma minus 1 and radius is 2 units. So in this radius of the region circle, we get a, this is minus 1 comma minus 1 is center, and given poles means that whatever the poles we are getting, that poles are inside or not, we have to check it. That is the pole z is equal to minus 1 minus 2i, that is minus 1 comma minus 2 point lie inside or lies inside the given circle mod z plus 1 plus I equal to 2. So now minus 1 comma minus 2, this is the point. X quadrant is, x value is minus 1 and y quadrant, y value is minus 2. So that is minus 1 comma minus 2 is inside the circle, and other point z is equal to minus 1 plus 2i, minus 1 comma 2 is lies outside the given circle. Why? Because of here minus 1 comma 2 is the outside of the given region. Minus 1 comma 2 is the outside the region. So inside we have only one pole, that is minus 1 minus 2i. This pole is inside. Z is equal to minus 1 minus 2i, and the point is minus 1 comma minus 2. This one is the inside the given region. So that's why we can find the residue at only one pole. That is also simple pole. So that's why formula is residue of f of z at z is equal to a equal to limit z tends to a z minus a into f of z. That is residue of f of z at z is equal to minus 1 minus 2i equal to limit z tends to minus 1 minus 2i of z. Here z minus a value is minus 1 minus 2i. That is z minus of minus 1 minus 2i. It becomes to z plus 1 plus 2i into f of z, z minus 3 by z square plus 2z plus 5. So already we discussed how to write the factors to the denominator. So then substitute that factors in the denominator. So one factor is z plus 1 plus 2i, that is cancel, and now you can apply the z limit, that is z tends to minus 1 minus 2i, that is substituted by z, that is minus 1 minus 2i minus 3 by z value is minus 1 minus 2i plus 1 minus 2i. Here plus 1 minus 1 cancel, we get minus 4 minus 2i by minus 4i. In the numerator minus common, minus minus cancel, 4 plus 2i by 4i. Then here we can write 4 by 4i plus 2i by 4i. Then here we get 4 cancel, 1 by I plus here I cancel, 2 cancel with 2 cancel in the 4, it is 1 by 2. Then again we have to write I square is equal to minus 1 and minus I square is equal to 1. So here we can write I is equal to minus I square, 1i cancel, we get 1 by 2 minus I. This is our required residue at minus 1 minus 2i. Then by using the residue theorem, integral over c f of z dz is equal to 2 pi I into sum of the residues. That is 2 pi I into, we have only one residue, substitute it, we get 2 pi I into 1 by 2 minus I. So means that by using the residues also we are evaluating the integration of f of z over the circle or any generally we discuss only circles. So we evaluate the integration by using the residue theorem, that is integral over c f of z dz is equal to 2 pi I into sum of the residues. This is the main concept for today.